Hello everyone, welcome back. In today's lecture, I am going to start a new chapter that is about the analysis of stresses and strain, and basically the points which I am going to discuss is stress of strays at a point, then stresses on inclined plane, principal stresses, then two-dimensional Mohr circle for stress analysis, then deformation and strain and stress of strain at a point. So let us start with our first topic, which is the stress state at a point. Now, the most of metal forming processes involve complex states of stresses and strain. In this chapter, we treat the analysis of stresses and strain right from the definitions. For that, let us first examine what comprises a complete state of stress at a point. The state of stress at a point comprises the stress vectors or component of stress vectors acting on three mutually perpendicular planes passing through the point. With the knowledge of these components of stress state, we are able to determine normal and shear stresses on any plane passing through the point. Here, figure shows the stress vectors SA, SB and SC. This is SA, SB and SC. Acting on three faces of a cubical element at a point P. This is our point P. Here and in the following, the vectors are denoted by bold letters. When the sides of the cubical element are reduced to 0, the three faces of the cube would pass through the point. The stress vectors acting on faces of cubical element may be decomposed into stress components acting in the direction of chosen coordinates. Thus, the stress vectors SA acting on the face ABCD is decomposed into three components, one along the normal to the face, while other two are parallel to the face but are directed along the other two coordinate axes. As you can see, this is our plane A, B, C and D. Now this SA is divided into three portions, that is, first is sigma xx over here, because this is our x, this is y and this is our z, perpendicular to this, which means it is x into sigma xz, and over here which means sigma x and y plane, here it will be in the xz plane. So in this way we can denote in the three direction of all the stresses. The stress vector acting on the faces of cubical element may be decomposed into stress component acting in the direction of the chosen coordinate, and thus the stress vector SA acting on the face ABCD is divided into three parts. The three components are denoted by this sigma xx, sigma xy and sigma xz. As we can see individually, if we look at here x, y and z, as SA is acting over here SA, so first it will be over here, so it will be sigma xy. For this plane it will be sigma xz, and for this plane it will be sigma xx. Note that the first subscript in all the three component is x, because these three components are acting on a plane which is perpendicular to the x-axis. The first subscript denotes the orientation of the normal to the plane on which the stress component is acting, and the second subscript gives the direction of stress component itself. The sigma xy is acting on the plane normal to the x-axis and is directed along the y-axis. Similarly, sigma xz is acting on the same plane but is directed along the z-axis. Thus, stress component on other two faces are also designated similarly. So, we see that with every component of stress, two directions are associated. From the above, it is clear that the stress state comprises 9 components as here shown in figure. For these 3 components for SB and 3 component for SC. Total 9 components. However, the 3 shear stress component sigma xy, xz and sigma yz are respectively equal to the 3 components sigma yz, sigma zx and sigma zy. So they are similar to this component are similar, these two components are similar and these two components are similarly. Thus we need to determine only 6 component, which is sigma x x x y x y y x z y z and z z to know the complete stress of state. In the following, in the view of convenience, we may take the axis as x1, x2 and x3 instead of x, y and z. In that case, there will be 9 component of stress state and denoted by sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32 and sigma 33. These components are in fact the components of second order symmetric stress tensor. The second order means there are 2 coordinates associated with each component, as we have already discussed above. It is symmetric because sigma 12 is equal to sigma 21, while sigma 13 is equal to sigma 31 and sigma 23 is equal to sigma 32. Therefore, we may denote the stress state at a point P by component of stress tensor capital T, which is given by this equation. So, this is about the stress state at a point. Next is stresses on an inclined plane. In this section, we determine stresses normal and shear on any plane passing through a point at which stress state is known. For that, consider a plane ABC inclined to the 3 Cartesian coordinate axes x1, x2, x3. Here you can see in the figure 3 axes x1, x2 and x3, and there is a plane A, B and C which intersects to the axis, and intersecting them at a point A, B, C respectively. Thus A, B, C and P forms a trapezoidal. This trapezoidal will be look like somewhat this. So this will be looking like a trapezoidal. P is over here, A, B and C. So it will look like a trapezoidal. The stress components acting on the three perpendicular faces of this trapezoid, which lie in coordinate plane, are the component of stress tensor or stress state at a point P and are completely known. We have to find the stress vector capital S acting on the inclined plane ABC. Let capital S1, S2, S3 be the magnitude of three components of vector S in the direction of coordinate axes. Here you can see there are three stress vector S1, S2 and S3 of this total component S. Let the AS be the area of the triangle face ABC and A1, A2, A3 be the area of triangle face BPC, CPA and APB. So AS is the area of this ABC triangle and other faces triangle area is A1, A2, A3. Now the trapezoid ABCP would be in equilibrium if the resultant force acting along the three axes are 0. So for that we can write by this S1 stress on the this plane and the area of this ABC is AS. So from that we have to minus the sigma 1 1. Well, you can see this sigma 1 is in this direction and which is acting on this plane, so it will be with the area of that plane is A1, sigma 2 1 is over here and sigma 3 1 is over here. The area of this plane is A1, this plane area is A2 and this plane area is A3. Similarly for three plane, the plane ABC should remain in equilibrium if these three S1, S2 and S3 are resolved in the similar way. Let the component of unit normal vector to the inclined plane ABC be the n1, n2 and n3 with respect to x1, x2, x3 respectively. Now the areas AS, A1, A2, A3 and component of the unit normal vector are related as by this equation. A1 by AS is equal to N1. These are the unit normal vectors. N1 is the, as you can see, the N1 is the unit normal vector. So for each and every we can find the area of the side plane to the area of our principal plane ABC. Now dividing the equation, these three equations by AS and substituting these three values in this equation, as we divide by AS we get S1, S2 and S3 as this by this equation, as we have divided by AS. Divide by AS to these three equations, we will get new equation as A1 by AS is equal to N1, A2 by AS is equal to N2 and A3 by AS is equal to N3. So in this way we will get this equations of S1, S2 and S3. Now from these equations we can say that any one of the three components of the vector S may be written as below, because sigma ij is equal to sigma ji. So Si is equal to sigma ij into nj. In the above equation, and in the following, a repeated subscript in a term means that there is a summation of the terms over the values of the subscript, and the right hand side of this equations is the sum of three terms formed of j is equal to 1, 2 and 3. The stress normal to the plane ABC, that is sigma n, is obtained by projecting the three components S1, S2, S3 on the normal plane. Thus, sigma n can be obtained by dot product of the vector S1, S2, S3, that is the S dot product of these three with unit normal vector small n. So sigma n is given by S into n, where we can say that the S is equal to S1 into E1, S2 into E2 and S3 into E3, and n is equal to n1 into E1, n2 into E2 and 3 into E3. So by sum of this we will get also the n1 square plus n2 square plus n3 square is equal to 1, because the unit vectors are there and the square and sum of the unit vectors will be 1, and E1, E2, E3 are the unit vectors along the x1, x2 and x3. The unit vectors for the planes is n1, n2, n3, while for the unit vectors for the axes are e1, e2 and e3. By substituting we get the sigma n is equal to S1 into N1 plus S2 into N2 plus S3 into N3. So we can say Si into Ni. By substituting for Si from the equation, we get a general relation for sigma n, and sigma n is equal to sigma ij ni into nj. As we know that the sigma ij we have to put the value, and the magnitude of s of the vector is given by s square is equal to s1 square plus s2 square plus s3 square. Now the shear stress component sigma s acting on plane ABC can be determined by this final equation: sigma s square is equal to capital S square minus sigma n square, and sigma n is equal to sigma I j n I into n j, and s is equal to s1 square plus s2 square plus s3 square. If we go on changing the orientation of the inclined plane, we shall come across a set of three perpendicular planes on which the shear stress are 0, and the planes are called as principal plane, and the normal stress acting on them are called as principal stresses. So if we go on changing orientation of the inclined plane, as we shall come across a set of three perpendicular planes on which the shear stress are 0, and these planes are called principal planes, where the for perpendicular planes the shear stress are 0 and the normal stress acting on them is called as principal stresses. The planes on which the stress is 0, that is called as principal planes. Now let us take the example for the same. The stress state at a point is given by stress tensor. The value of stress tensor is given. Determine the normal and shear stress component on a plane which is equally inclined to the three axes. The unit of stresses is Newton per mm square. Here sigma, the direction of cosine of normal to the plane equally inclined to three axes are given by equally inclined, which means the direction cosine will having 1 by root 3, 1 by root 3, 1 by root 3. This will be the value of inclination of the three axes for equally inclined plane. The normal shear stress is given by this equation sigma n, sigma ij ni into nj. So if we put the value of this in this equation, here the all tensure are written as the sum divided by 3. So we will get the sigma n, and the component of S1, S2, S3 of vector S are determined as the component of S1, S2, S3 are written by sigma 11 into N1 plus sigma 21 into N2 plus sigma 31 into N3. So in this way we can write the S1, and similarly we can find the value of S2, S3 and S square, as we know that. So from S we can find sigma S, as we know that is S minus sigma S square minus sigma n square. So as we know that sigma S square is equal to S square minus sigma n square. So sigma S will be S minus sigma n. Here it will be 1 by 2. So from sigma S we can find the shear stress on the given plane. So this is the final answer. This is it for today's lecture. Thank you very much for listening me carefully. Have a nice day.